In the quiet of nebulae, cold gas and fine dust drift in darkness that looks empty and yet grows heavy. And within this hush, gravity gathers what seems loose into shapes that learn to hold their own weight. Giant molecular clouds wrapped in dust that shields them from harsh starlight rest at temperatures near 10 to 20 Kelvin. In this chill, atoms move slowly. Pressure weakens, and the balance tips toward collapse when a pocket grows dense enough for gravity to win. The darkness is not absence, it is cover. Dust grains that block the visible glow of distant stars also keep the interiors cool, and by keeping them cool, they permit the inward slide that brightness will one day announce. Across these clouds, long filaments extend like threads laid by a slow hand, and where filaments meet, hubs collect material that becomes the seeds of clusters. Turbulence stirs the gas, lending momentary support while also compressing it into denser knots, so resistance and invitation coexist in the same flow. Magnetic fields thread the whole, guiding motion and slowing collapse in some directions while feeding it along others. Under these conditions, a region that crosses the threshold where self-gravity overwhelms pressure and support becomes gravitationally unstable and begins to fall inward in a patient, accelerating quiet. Cooling makes collapse possible. Hydrogen molecules form on the surfaces of dust grains when single atoms briefly settle and combine, and those molecules let the gas radiate energy away so that it can sink deeper into the potential well without heating enough to stop. Carbon monoxide adds its lines to the spectrum, a radio whisper that betrays the cold. Cosmic rays slip through and maintain a thin thread of ionization, tying the neutral gas to magnetic fields so that drift and drag play out over long times. The dance is gentle, but the outcome is steady. Density rises, the free-fall time shortens, and the center grows heavy. As a core gathers mass, it turns from translucent to opaque, and radiation finds fewer paths to leave. A small warm center appears and expands, not in a burst but as a consequence of continued infall, and the infalling gas becomes a rotating disk because angular momentum, however modest, refuses to vanish. Material spirals through that disk toward the center. To conserve the momentum it cannot keep, the newborn object launches narrow bipolar outflows and jets along its poles, which burrow through the envelope and carry away energy and angular momentum while barely disturbing the overall hush. The first nuclear steps wake softly. Deuterium burning lights at a lower temperature than hydrogen fusion, and briefly slows the contraction, a quiet plateau while the young star moves toward hydrostatic balance. Soon pressure and gravity reach a truce on the main sequence, but that long calm is already conditioned by what the core has accumulated. Stars rarely form alone, clusters are common, and multiplicity is not an exception but a norm. In this crowded beginning, separations shrink under gravity, or widen under ejections, and close companions set up later exchanges of mass that will shift endings still far ahead. Composition shades the script. Gas with fewer heavy elements cools differently and fragments into different mass scales. Dust abundance changes chemistry and opacity. Rotation redistributes infall. An environment sets how quickly stellar feedback cuts off supply. The initial mass function, a statistical curve that counts many small stars and fewer large ones, appears with remarkable regularity across galaxies, yet the precise mix of drivers that shapes it remains unsettled. The efficiency with which a cloud turns mass into stars also sits low, only a small fraction by the time winds, radiation, and supernova disperse what remains. Three quiet ironies rest here. The darkest places in a galaxy give rise to the brightest lights. Cold makes heat possible, because only chilled gas can release enough energy to condense toward the temperatures where fusion begins. collapse builds structure by erasing space, gathering material inward by thinning the volume that held it apart. Each is simple, each is steady, and each turns absence into form. A single, unadorned fact follows from these balances. A star is born when self-gravity in a cold, dense region overcomes thermal pressure and other supports, and the resulting collapse forms a protostar plus an accretion disk that feed one another until a stable, fusing star appears. A small, lesser-known detail rides on the smaller surfaces. Dust grains in the cold acquire icy mantles of water, carbon monoxide and simple organics, and as the center warms, those mantles evaporate to lace the gas with molecules that glow in millimeter light. A quiet uncertainty remains beside them. How precisely the stellar initial mass function emerges with such similar shape in so many places, and how turbulence, magnetic fields, radiation, and environment conspire to set the mass that any given core will finally keep. Seen in infrared, the filaments resemble slow rivers, and the hubs look like confluences. Time stretches, because a single collapse can take hundreds of thousands of years, and the assembly of a cluster can fill millions. Nothing hurries, and yet nothing waits. The same dust that hides the core from view becomes the material that later scatters starlight into wide reflection nebulae. The envelope that muffles heat becomes the gift that carries it. A core growing towards several solar masses is restless even now, collecting supply along the filaments that fed it, while a smaller core nearby settles sooner into its truce. The former carries the quiet premise of a future supernova, and the other does not. And both rest together while gravity rehearses what comes next. The broad answer to the question of ending settles, softly, at the moment of beginning. Mass gathered now will decide whether the later heart can support itself when fusion runs out of ways to pay for weight. Rotation and magnetic fields will shape how matter reaches the center. Metallicity will govern cooling and opacity. Companions will offer or withdraw supply, and later, in tight orbits, they may return to change the balance again. No star intends an ending, it follows gradients. Yet in this cold room of dust and hydrogen, the quiet difference between a tranquil retirement and a luminous unbinding already exists as a number that rises or stays small. For now, the number grows in some places and rests in others. For now, the gas keeps falling, and the disk keeps turning, and the outflows keep carving lanes through the envelope. For now, beginnings and endings are the same sentence written at different speeds, and both are present in the hush that lets the future form. The weight that shapes a star begins as a quiet sum of countless small arrivals, atoms and molecules drifting inward along the slow pull of gravity, until they are claimed by a forming core. In this gathering there is no urgency, only the steady transfer of matter from cloud to center, and in this accumulation the future is decided with a precision that feels both inevitable and without intent. Mass is the governing quantity. A star born with less than about 8 times the mass of the Sun will never reach the internal pressures and temperatures needed to forge an iron core. And so it will live long, burn gently, and end in quiet collapse to a white dwarf. A star that begins with more than this threshold will progress through heavier fuels, push to extremes, and eventually exhaust every way to balance its own weight, ending in collapse and a supernova. Between these limits, mass determines temperature, luminosity, lifetime, and the path through the sequence of fusion stages. The nuclear rate is sensitive to temperature in a way that magnifies small differences, so the most massive stars consume their reserves at a furious pace, living only millions of years, while the least massive sip their fuel slowly over spans longer than the current age of the universe. The geometry of this balance is shaped early, before the star has even reached the main sequence, as accretion feeds the core. In binary or multiple systems, the initial mass is not always final. Companions can transfer mass, altering the course of evolution and even the ultimate fate. Rotation also leaves its mark. A star spun up by accretion or born with rapid rotation can mix its interior more efficiently, keeping fresh fuel near the core and prolonging certain burning phases. Metallicity, the fraction of mass in elements heavier than helium, influences cooling rates and opacity. Stars in the early universe with near-zero metallicity are thought to have formed more massive on average because their gas could not cool as effectively and fragment into many small stars. The first quiet irony is that more mass leads to a shorter life, so the most luminous stars vanish soonest, leaving the faint to endure. The second is that the ultimate violence of a supernova is decided not at the moment of collapse, but in the stillness of the star's youth when its mass is set. The third is that stability is maintained for most of a star's life by the very fusion reactions that steadily undermine its future by altering its composition and moving it toward a state it cannot escape. A core fact rests at the center of this balance. The inward pull of gravity is resisted by the outward push of pressure generated from nuclear fusion in the core, and the mass of the star sets the scale at which this balance can be maintained and for how long. A lesser-known detail is that above certain mass thresholds, strong stellar winds driven by radiation pressure peel away the outer layers, reducing the final mass before collapse, and sometimes changing the type of supernova or compact remnant that will result. Yet uncertainties remain. The exact mapping between initial mass and final fate is blurred by mass loss rates that depend on metallicity, magnetic fields, rotation, and binarity. Predictions for the most massive stars vary, and the role of episodic eruptions or mergers in altering these fates is not yet fully known. Observations of progenitor stars for supernovae have filled in parts of the diagram, but have also revealed exceptions that resist simple classification. In clusters, the distribution of stellar masses follows a statistical pattern known as the initial mass function, and while this curve is nearly universal in shape, the physical processes that fix its form are still debated. For massive stars, there is also the question of how much mass they lose in the last stages of life through winds or eruptions, and whether these outflows prepare the surrounding space in ways that help or hinder the later supernova shock. Across a stellar nursery, the same physics unfolds in parallel with different weights. A star forming at the low end of the mass range will spend hundreds of millions to billions of years in stable hydrogen burning, changing little in appearance, while its massive neighbour evolves through its fuel in only a few million years, swelling and changing colour, moving through burning stages that will pile ashes of heavier elements in its core. The low-mass star will outlive not only its massive sibling, but also any record of that sibling's existence beyond the enrichment of the surrounding interstellar medium. The pathway from birth mass to final act is a line drawn without haste but with no erasing. Each gram that falls inward during formation becomes part of a total that will decide pressures, densities, and temperatures billions of years later. Companions can change this line. In close binaries, mass transfer can strip the hydrogen envelope from a star, exposing helium layers and leading to stripped envelope supernovae of type Ib or Ik. In other cases, accretion can push a star or a white dwarf over a limit, triggering collapse or thermonuclear runaway. These interactions make the role of mass more complex, as the initial value is not the only one that matters. The difference between ending as a white dwarf or as a neutron star or black hole lies in a range that can be narrow, and it is sensitive to details in the history of the system. Observations across the galaxy show that massive stars tend to form in clusters and associations, meaning that their evolution and final explosions are part of a collective shaping of the interstellar medium. Stellar winds carve cavities in surrounding clouds, ionizing and compressing gas that can trigger new star formation even before the first supernova occurs. In the larger view, the distribution of stellar masses in a generation of stars determines the timing and scale of feedback into the galaxy. High-mass stars provide intense ultraviolet radiation, mechanical energy through winds, and finally the shock waves and chemical enrichment of supernovae. Low-mass stars offer quiet persistence and long-term stability, seeding the galaxy with their light over timescales that high-mass stars will never reach. In this, mass is the quiet architect of both an individual star's destiny and the collective evolution of its host galaxy. Even now, in distant stellar nurseries, cores are forming that will carry within them the weight that defines their futures. Some will never approach the threshold for core collapse and will fade into white dwarfs. Others, carrying enough mass to forge iron in their centers, will one day pass beyond the point where fusion can resist gravity. The difference lies not in choice but in the arithmetic of accumulation, a slow sum begun in the cradle of dust and gas. The cloud does not know it is writing futures, yet the numbers hold, and the outcomes are steady. A star's mass is its measure of time, its scale of light, and the form of its final silence or its final shout. The slow dance of fusion begins once the inward weight of gravity has compressed the core to the point where temperatures reach about 10 million Kelvin and hydrogen nuclei, stripped of their electrons, move fast enough to overcome the mutual repulsion of their positive charges and merge. In this state, matter exists as plasma, a fluid of free protons and electrons moving in dense hot patterns, and each successful collision between protons releases energy in the form of gamma-ray photons and neutrinos. In stars with masses similar to or less than that of the Sun, the dominant pathway is the proton-proton chain, a sequence of reactions in which hydrogen gradually becomes helium through a set of intermediate steps. In more massive stars, where core temperatures exceed about 15 million Kelvin, the carbon-nitrogen-oxygen cycle becomes the primary route, using existing carbon nuclei as catalysts to fuse hydrogen into helium more quickly. Both processes convert a small fraction of the mass of the fuel into energy, according to the relationship described by the equation of mass-energy equivalence, and this energy flows outward through the layers of the star. The core fact of this phase is that the rate of fusion is highly sensitive to temperature, increasing dramatically with even small rises, which means the star naturally adjusts its internal structure to maintain balance between outward pressure from fusion-generated heat and the inward pull of gravity. In main sequence stars, this balance, called hydrostatic equilibrium, can last for millions to billions of years depending on mass, with little change in the star's outward appearance. A lesser-known detail is that the photons released in the core do not travel outward at the speed of light to the surface. Instead, they are repeatedly absorbed and re-emitted by surrounding particles, wandering in a random walk that can take hundreds of thousands of years before the energy finally escapes as visible light. During this time, the identity of the individual photons is lost, but the flow of energy remains steady. The first quiet irony is that the light we see from a star today began its journey deep inside long before any living observer existed to witness it. The second is that the fusion that sustains a star's life is the same process that moves it step by step toward the conditions that will end it. The third is that the outward steadiness of a main sequence star hides the ceaseless, chaotic collisions and transformations in its heart, where countless reactions occur every second without ever disturbing the calm seen from afar. Fusion in the core also produces helium ash, which accumulates because the temperatures and pressures are not yet high enough to fuse helium further. Over time, this buildup changes the core's composition and density, slowly altering its structure. In massive stars, convective mixing can carry some helium outward while bringing fresh hydrogen inward, extending the period of stable burning. In smaller stars, convection may occur throughout the interior, thoroughly mixing the composition and burning hydrogen more uniformly. Still, no mixing process is perfect, and eventually the hydrogen in the core is depleted. When this occurs, the star must adjust. For lower mass stars, the core contracts under gravity, heating until helium fusion can begin in a process known as the helium flash, while hydrogen fusion continues in a shell around the core. In massive stars, the contraction after core hydrogen exhaustion leads seamlessly into the next stage of burning, with hydrogen fusion in a shell and helium fusion beginning in the core without the need for a flash. This progression is dictated entirely by the star's mass and composition, and the exact path differs for solitary stars and those in binary systems where mass transfer or tidal effects alter evolution. Yet, mysteries remain. While the basic sequences of fusion are understood and well tested in laboratory experiments and stellar models, the detailed behavior of convection, mixing, and rotation within real stars is difficult to measure and model precisely. The degree to which rotation-induced mixing can extend main sequence lifetimes, especially in massive stars, is still a topic of active research, as is the influence of magnetic fields on internal flows. Observations of surface abundances in evolved stars sometimes reveal levels of certain elements that suggest more mixing than models predict, hinting at processes not yet fully captured. The pace of the slow dance is set by the need for balance. If fusion proceeds too quickly, the core expands and cools, reducing the reaction rate. If it slows too much, the core contracts, heating and raising the rate again. This self-regulating behavior is why main sequence stars remain stable for such long stretches of time. In the largest stars, the luminosity approaches the Eddington limit, where the outward force of radiation on the stellar material is nearly enough to counteract gravity at the surface, and this drives strong stellar winds that carry mass away. These winds, while seemingly peripheral to core fusion, can shape the future by reducing the mass available for later burning stages and altering the mass of the eventual remnant. The fusion that now appears steady will one day run out of hydrogen fuel in the core, and that will mark the first major structural change in the star's life since its birth. But in the long main sequence phase, this change feels infinitely far away. Billions of years can pass for a low-mass star without appreciable difference, while for a high-mass star, only a few million years separate the beginning of hydrogen burning from its exhaustion. Across these differences, the same principle applies. The star exists in a state where gravitational contraction is exactly balanced by the pressure from nuclear fusion, and the energy released maintains both the structure of the star and the radiation that travels outward into space. From the perspective of the galaxy, the main sequence is a prolonged moment of calm in which the star's role is to convert hydrogen into helium while quietly setting the stage for what follows. This stage is where most stars spend the majority of their lives, so it dominates the population seen in surveys. In the heart of each, the slow, precise steps of fusion continue without pause, each reaction adding to the helium core, each photon beginning a long journey outward, each neutrino passing through the star and into space almost without interaction. The energy produced drives the circulation of matter within the star, powers the winds that strip mass, and sets the boundaries for all later stages. In this way, the slow dance is not only a matter of physics within the core, but also a shaping of the star's relationship with its surroundings, influencing the interstellar medium and, in massive stars, preparing the ground for the violent transformation to come. For now, the balance holds. The core remains hot enough, the density high enough, and the fusion steady enough to maintain the star's luminous surface. The gentle truth is that while each reaction is fleeting, the sum of them across deep time becomes the enduring light of the star, and in that light the stillness of the dance is preserved. Layer upon layer of fire builds in the heart of a massive star as it moves beyond the steady simplicity of core hydrogen burning. When the hydrogen in the core is exhausted, fusion shifts outward into a shell surrounding a core now composed almost entirely of helium. Gravity pulls the core inward, increasing its temperature and density until it reaches the threshold for helium fusion. In massive stars, this transition is smooth, without the sudden onset that occurs in low-mass stars, and the helium ignites in the triple alpha process, where 3 helium nuclei combine to form carbon, with some carbon nuclei capturing an additional helium nucleus to form oxygen. The heat from helium fusion halts the core's contraction for a time, and the star settles into a new equilibrium, though one that is shorter-lived than the hydrogen burning phase. As helium in the core is depleted, burning moves outward into another shell, and the core contracts again, igniting carbon fusion at still higher temperatures. This progression continues through neon, oxygen, and silicon burning, each stage requiring greater temperatures and each lasting for a shorter time than the one before. Silicon burning is the briefest, lasting only days in the most massive stars, and produces an iron-nickel core that marks the end of exothermic fusion. The essential fact here is that each new fusion stage occurs in a shell around the inert core, with the structure of the star resembling a cosmic onion, layers nested within layers, each a different burning region producing its own set of elements. A lesser-known detail is that the boundaries between these shells are not perfectly distinct. Mixing processes such as convection and instabilities can blur them, and in some cases shell burning can become unstable, with pulses of fusion that briefly alter the star's luminosity. The first quiet irony is that the most advanced and complex structures inside a star appear just before its destruction. The second is that the very layers of fire that sustain the star's luminosity in its last days are producing the conditions that guarantee its end. The third is that while the outer layers may swell to supergiant dimensions, cool enough to appear red to an observer, the true furnace grows smaller, denser, and hotter at the center, retreating from view. Between each burning stage, the core contracts as fuel is exhausted, raising the temperature enough to ignite the next stage, while the outer layers respond by expanding or contracting in turn. In red supergiants, the radius can grow to hundreds of times that of the Sun, with luminosities tens of thousands of times greater. Yet the outer envelope is tenuous, and most of the star's mass remains in the deep interior. In blue supergiants, the outer layers stay more compact, but the internal sequence of burning shells is similar. Each stage of fusion after helium is shorter, because the energy released per unit mass decreases as heavier nuclei are formed, and the core must burn more quickly to support the weight above it. By the time silicon burning begins, the timescales have shortened so much that the structure is changing on timescales of days, a final rush toward collapse. The quiet mystery lies in the exact behavior of these burning shells, especially in the final days and hours. Multi-dimensional simulations show that turbulence, convection, and waves generated by burning can transfer energy into the envelope in complex ways, possibly influencing mass loss before collapse. Observational evidence for such pre-supernova mass ejections has been found in some cases, but the processes that drive them remain uncertain. These layers also determine the chemical yields of the eventual supernova. Elements from carbon to iron are distributed throughout the shells, and the shock wave from the explosion will mix and eject them into space. The precise structure at the moment of collapse influences how much of each element escapes and how much falls back into the compact remnant. In some massive stars, strong stellar winds during earlier stages have already removed much of the hydrogen envelope, producing a Wolf-Rayet star with exposed helium or heavier layers. These stripped stars still build their onion-like cores, but may explode as stripped envelope supernovae, their spectra lacking hydrogen and sometimes helium lines. In other cases, mass transfer in a binary system removes the envelope. The outer appearance of the star may differ greatly, but the interior sequence of shell burning is shaped by the same physics of pressure, temperature, and nuclear reaction rates. The structure of the shells also affects the propagation of the supernova shock. A dense core surrounded by a tightly bound mantle can absorb much of the shock energy, possibly leading to a weak explosion, or even collapse directly into a black hole without a bright supernova. Conversely, a more extended, loosely bound envelope allows the shock to expand more easily, producing a luminous display. The star's last centuries, decades, and days are a steady progression through these burning stages, yet to an outside observer the changes are subtle until the final moment. Neutrinos stream from the core during each burning phase, carrying away energy and cooling the star in ways that influence the timing of each stage. These neutrinos are almost impossible to detect until the burst that accompanies core collapse, yet they are a constant background to the star's life. In the slow approach to the end, the layers grow in number, the core grows in density, and the time left grows short. The shell structure is a record of the star's entire nuclear history, each layer a frozen moment in the chain of fusion that has transformed the primordial hydrogen and helium into a palette of heavier elements. When the final stage of silicon burning ends, the core is composed mostly of iron and nickel, nuclei that cannot release energy by further fusion. At this point, gravity has no counterbalance from nuclear processes, and the path to collapse is unavoidable. Yet in this layered structure, so intricate and so close to failure, there is a stillness. The outer layers remain luminous, the star still radiates as it always has, and no visible sign betrays the imminence of the event. The irony deepens. The most complex internal architecture of the star exists in the instant before gravity overwhelms it, and that architecture will survive only moments longer before being unmade in the blast. This layered arrangement is both the pinnacle and the prelude, a quiet culmination of fusion's slow work and the fragile final state from which no return is possible. The iron that refuses to burn forms in the innermost heart of a massive star as the last step in the sequence of core fusion. Silicon burning, the final exothermic stage, assembles iron group nuclei such as iron 56 and nickel 56 in the densest, hottest core the star will ever hold in hydrostatic balance. The physics here is absolute. Fusing elements heavier than iron does not release energy, but instead requires it, because the binding energy per nucleon reaches its maximum at iron. Once the core becomes predominantly iron, there is no further nuclear pathway that can generate the outward thermal pressure needed to support the weight above. Gravity has been countered for millions of years by the heat from fusion, but with the arrival of iron, that counterweight is gone. The core contracts, heating further, but no amount of heat can ignite a new stage of fusion that yields net energy. In this stillness before collapse, the iron core grows as silicon burning shells feed it from above, the mass increasing toward the Chandrasekhar limit for a degenerate electron gas, around 1.4 times the mass of the Sun. In this state, the electrons are squeezed into their smallest quantum states, providing degeneracy pressure that temporarily supports the core. A lesser-known detail is that during silicon burning, the reactions produce nickel 56, which decays after the supernova into cobalt 56 and then iron 56, and this decay will power the light curve of the explosion long after the initial flash. The first quiet irony, is that the element that ends the star's life in its core is the same element it will later scatter through space to build planets and living worlds. The second is that the most stable nucleus, iron, becomes the point of greatest instability when it dominates the core. The third is that in its final growth, the iron core is sustained not by the energy of fusion, but by the quantum mechanical refusal of electrons to be compressed further, a support that will fail catastrophically. As the core mass approaches the limit, two processes hasten the end. Photodisintegration occurs when high-energy gamma rays break iron nuclei into lighter particles, consuming energy and reducing the pressure. Simultaneously, electrons are captured by protons in nuclei, forming neutrons and releasing neutrinos in vast numbers. These neutrinos stream outward, carrying away energy and further cooling the core, eroding what little support remains. The electron captures also remove the pressure that degeneracy provided, triggering a runaway collapse. The time from the onset of these processes to complete collapse is measured in less than a second. Yet the approach is slow in geological and stellar terms, with the final weeks, days, and hours marked by a steady increase in neutrino emission and subtle shifts in the core's density profile. The quiet mystery lies in the exact structure of the iron core at the instant before collapse. Multi-dimensional simulations reveal that convection, rotation, and asymmetric flows shape the density and temperature, and these may influence how the shockwave forms and whether it succeeds in expelling the star's outer layers. Observations of neutrinos from a future nearby supernova would offer the only direct probe of these final moments, but such an event has not occurred in our era of modern detectors. For now, the models and indirect evidence from supernova remnants form the map. Above the iron core, the layered shells of lighter elements continue their own burning, but these outer stages are disconnected from the immediate crisis in the center. When the core collapses, the shock wave will travel outward through these shells, altering and mixing them before they are cast into space. In stars with especially high mass, fallback of material onto the compact remnant may swallow much of the heavy element yield, forming a black hole with little or no visible supernova. In other stars, the explosion will unbind most of the envelope, leaving behind a neutron star. The outcome depends sensitively on the core's mass, structure, and rotation, as well as on the uncertain physics of how the collapse is reversed into an explosion. In this last stage of stability, the iron core is silent. It does not shine. The photons produced cannot escape the overlying layers, and the neutrinos pass unnoticed. The star's surface still glows as it has for millennia, and from far away there is no hint that the central balance has failed in principle, awaiting only the final shift in numbers to begin the fall. The inward pressure of gravity and the lack of any further fusion fuel form an equation that will be solved instantly when the Chandrasekhar limit is exceeded. The contraction will proceed at a fraction of the speed of light, densities rising past that of atomic nuclei, and the matter will transition into a sea of neutrons. For the outer layers, the collapse will be a wave racing inward. For the core, it is the end of motion except for the quantum structure of nuclear matter. The final iron core is not large in size, about the diameter of Earth, but it contains more mass than the Sun. Its density, on the verge of collapse, is already staggering, and its composition is uniform in its inability to produce further energy. The approach to this state is the work of millions of years of fusion and layering, yet the duration of the state itself is measured in seconds before the collapse begins. The irony is complete. The most stable form of matter at the nuclear level is the least able to resist gravity's pull at the stellar scale, and its perfection in binding energy becomes the condition for the star's destruction. In these last instants before the fall, the physics is settled, the sequence determined. What follows will be violent, brief, and transformative, scattering the iron that was the undoing of the star into the galaxy, where it will join clouds of gas and dust, condense into new worlds, and perhaps become part of the cores of planets, the blood of living creatures, and the tools that observe the light from distant supernovae. The same element that ended the star's life will carry forward into the lives of others, a quiet cycle hidden in the calm face of the star until the instant the balance fails. Collapse without warning begins in the instant when the iron core of a massive star surpasses the limit where electron degeneracy pressure can no longer support its weight. The loss of support is sudden, triggered by the combined effects of photodisintegration and electron capture, and once these processes take hold, there is no gradual shift, only a plunge. Inward motion accelerates to a significant fraction of the speed of light, and the core's matter compresses to densities exceeding that of an atomic nucleus. Protons and electrons merge into neutrons, releasing an immense burst of neutrinos. This transformation happens in less than a second, so quickly that the outer layers of the star are still falling inward, unaware of the catastrophe already underway at the center. The core's collapse halts abruptly when nuclear densities are reached, and neutron degeneracy pressure, along with repulsive nuclear forces, resists further compression. The sudden stop sends a shockwave outward through the still-in-falling material. This shock initially carries enormous energy, but it loses strength as it plows into the dense layers above, especially as it expends energy in dissociating heavy nuclei into free nucleons. Without some means of re-energizing it, the shock would stall, and the collapse would end not in an explosion, but in the quiet formation of a black hole or a neutron star without a luminous supernova. A lesser-known detail is that the initial shock always stalls in simulations of core collapse supernovae, and the leading explanation for how it is revived is the deposition of energy from the flood of neutrinos escaping the proto-neutron star. These neutrinos, produced in staggering numbers, about 1058 in total, carry away most of the gravitational energy released in the collapse, but a small fraction of them are absorbed in the material just behind the shock, heating it and driving it outward again. The first quiet irony is that the most powerful visible explosions in the universe rely on particles that barely interact with matter. The second is that the collapse that destroys the star is the same event that halts the collapse of the core, the reversal contained in the act itself. The third is that the majority of the energy released in a supernova is not in light, but in the invisible flood of neutrinos passing through the galaxy in silence. The collapse is accompanied by a burst of gravitational waves as the core's mass distribution changes, especially if the collapses are symmetric due to rotation or convection. These ripples in space-time carry information about the dynamics of the core, but they are faint and have only recently become detectable for some events. The quiet mystery lies in the precise combination of processes that determine whether the stalled shock is successfully revived. Multi-dimensional models show turbulent convection, standing accretion shock instabilities, rotation, and magnetic fields all influencing the outcome, but their interplay is not fully understood. Observations of neutrinos from a nearby supernova, as in the case of SN 1987A, provide rare and invaluable constraints, yet the details remain beyond direct observation for most events. As the revived shock moves outward, it accelerates through the layers of the star, interacting with shells of different composition and density. These interactions create instabilities that mix material, ensuring that elements forged deep inside are distributed throughout the ejector. The surface of the star brightens only when the shock reaches it, a phenomenon known as shock breakout, releasing an intense flash of ultraviolet and X-ray radiation that lasts minutes to hours. For a distant observer, this marks the first visible sign that the star has died. but the true death occurred seconds earlier in the core. In some stars, especially those that have lost their hydrogen envelopes, the breakout may occur in a much more compact outer layer, producing a shorter, harder burst of radiation. In red supergiants with extended envelopes, the breakout can be longer and cooler, with a more gradual rise to peak optical brightness. The aftermath of the collapse leaves behind a compact remnant. If the mass of the core after the explosion is below the maximum supported by neutron degeneracy pressure, it becomes a neutron star, a city-sized sphere of nuclear matter with densities beyond anything found elsewhere in the universe. If the core is heavier, it will collapse further into a black hole, an object from which nothing can escape. Which outcome occurs depends on the initial mass of the star, the amount of fallback after the explosion, and the details of the explosion mechanism. In some cases, the shock may fail entirely, and the collapse proceeds directly to a black hole without a bright supernova, an event called a failed supernova. Observations of red supergiants that vanish without a visible explosion suggest this pathway is real, though rare. In the moments of collapse and shock revival, the structure of the star's interior, carefully built over millions of years, unravels in seconds. Each layer is accelerated outward, shocked, and mixed. Heavy elements beyond iron are created in the most extreme conditions, either in the supernova itself or in the winds from the protoneutron star through rapid neutron capture. These newly made nuclei join those formed earlier in the star's life to enrich the surrounding interstellar medium. For now, the collapse is complete. The core has become either a neutron star or a black hole, and the energy released in neutrinos has decided whether the outer layers will be expelled or swallowed. The explosion, if it occurs, will shine for weeks to months as the expanding debris cools and the radioactive decay of nickel-56 powers its fading light. Yet the central act, the collapse without warning, remains invisible to almost every form of light, revealed only in the faintest of messengers, neutrinos, gravitational waves, and the eventual shock breakout at the surface. In the scale of the star's life, this moment is infinitely brief, but it is the pivot on which everything turns. The same mass that determined the star's fate at birth has now been weighed against the limits of pressure and found too great to bear. The fall is total, the change irreversible, and the space that held a stable star, a heartbeat ago, now holds either the most compact matter in the cosmos or the emptiness of a gravitational well from which nothing can return. The breath of neutrinos begins in the collapsing core, where matter is squeezed to densities beyond that of atomic nuclei, and temperatures rise to billions of Kelvin. In these conditions, protons and electrons are driven together into neutrons, and each reaction releases an electron neutrino. For a fraction of a second, the core becomes the brightest neutrino source in the universe, producing on the order of 10 to the power of 58 neutrinos of all flavors. They pour outward in every direction, almost all of them passing through the outer layers of the star and into space without interacting. The sheer number is so great that even the minuscule chance of interaction deposits a measurable amount of energy in the infalling stellar matter, and it is this small fraction that is thought to help revive the stalled shock wave. The essential fact here is that neutrinos carry away about 99% of the gravitational energy released during core collapse, with only about 1% going into the kinetic energy of the explosion, and a far smaller fraction into light. A lesser-known detail is that the neutrino burst emerges over roughly 10 seconds, with the first sharp spike called the neutronization burst, dominated by electron neutrinos from the initial electron captures, followed by a sustained emission of all neutrino flavors as the protoneutron star cools. The first quiet irony is that the visible light of a supernova, dazzling across galaxies, represents only the thinnest surface of the energy released. The second is that the particles responsible for driving the explosion in many models are those that almost never touch matter at all. The third is that the only confirmed direct detection of neutrinos from a supernova so far, from SN 1987A, amounted to just 24 events in terrestrial detectors. Yet these few particles carried more information about the collapse than the light that followed. As the protoneutron star radiates neutrinos, it cools and contracts, settling into a stable neutron star if its mass is below the maximum, supported by neutron degeneracy pressure. The outflow of neutrinos in the first seconds is intense enough to carry away about 1/10 of the mass energy of the Sun, released as pure radiation of a kind that does not heat or light anything in the way photons do. These neutrinos emerge from a surface called the neutrinosphere, analogous to the photosphere of a star, where the density drops enough that neutrinos can escape without further scattering. The neutrinosphere lies deep within the protoneutron star, and the conditions there, temperatures of tens of billions of Kelvin, set the energy distribution of the escaping particles. The quiet mystery lies in exactly how neutrino heating operates to revive the shock. In some simulations, turbulence behind the shock traps neutrinos long enough to deposit sufficient energy. In others, instabilities in the standing shock wave amplify the effect. There is also evidence that strong magnetic fields and rapid rotation can channel neutrino emission in ways that alter the dynamics, perhaps leading to the highly energetic explosions observed in some rare events. Neutrino oscillations, the quantum phenomenon in which neutrinos change flavor as they propagate, add further complexity, potentially altering the heating rate in the matter just behind the shock. For an observer on Earth, a nearby core collapse supernova would first announce itself in a rush of neutrinos hours before the shock breakout made the event visible. Modern neutrino detectors are prepared for this early warning, and even a few dozen detected neutrinos can pinpoint the approximate time and location of the explosion. The neutrinos' near light speed journey is almost unaffected by the matter they pass through, allowing them to carry pristine information about conditions in the core that photons cannot escape from. Yet for the star itself, the breath of neutrinos is not an announcement, but a release. It is the outflow of the energy that gravity extracted from the matter in collapse, the means by which the protoneutron star cools and the explosion is driven. Without them, the shock would not gain the energy needed to unbind the outer layers, and the collapse would end quietly in the dark. The first seconds after core bounce are a balance between accretion of infalling matter and outward neutrino heating. If the heating wins, the shock expands outward, accelerates, and passes through the shells of lighter elements, mixing them and ejecting them into space. If the heating loses, the shock recedes, the protoneutron star accretes more matter, and the core collapses into a black hole. The final outcome hinges on details of the neutrino emission, the density structure of the star, and the timing of instabilities. Once the explosion is underway, neutrino emission continues as the protoneutron star cools over tens of seconds, radiating away residual heat until it reaches a stable radius of about 10 kilometers. In some cases, winds driven by neutrino heating from the surface of the protoneutron star can synthesize heavy elements through rapid neutron capture, adding to the nuclear synthesis from the explosion itself. These winds depend on the neutrino luminosity and the conditions in the outflow, and their contribution to the chemical evolution of galaxies remains an open question. For the interstellar medium, the neutrinos leave no lasting trace beyond the role they played in unbinding the star. For the compact remnant, they mark the end of the violent transition from collapsing core to stable neutron star or forming black hole. In the scale of cosmic events, the breath of neutrinos is over almost before it is noticed. yet its effects ripple outward in the shock wave, in the elements scattered into space, and in the gravitational waves that may accompany asymmetries in the emission. The irony of their role is that they carry almost everything, give almost nothing to the light we see, and yet may decide whether the event we call a supernova ever occurs at all. To the star, they are the invisible breath that turns collapse into explosion, the final release of the gravitational binding energy it has held in reserve since birth. The unbinding of a star begins when the revived shock wave, strengthened by neutrino heating and turbulent motion behind its front, gains enough energy to push through the overlying layers that had been collapsing inward only moments before. As the shock travels outward, it passes through shells of distinct composition, left by the star's lifetime of fusion, each layer offering its own resistance, and transforming the energy of the shock in different ways. In the silicon shell, heavy nuclei are shattered into lighter components, consuming energy, but also creating the raw material for further nuclear synthesis in the expanding matter. In the oxygen and carbon shells, the sudden compression and heating trigger explosive burning, forging new elements in fractions of a second. The hydrogen and helium layers, if still present, are accelerated outward into the surrounding space, where they will expand for years to come. The essential fact of this stage is that the energy released in the explosion, though only about 1% of the gravitational energy liberated in the collapse, is sufficient to overcome the gravitational binding energy of the entire star outside the compact remnant. A lesser-known detail is that the shock does not simply pass cleanly through these layers. It induces hydrodynamic instabilities that cause mixing, so that heavy elements from the deep interior are dredged up into the outer ejector, and lighter elements are pushed inward in plumes and fingers. This mixing will later affect the light curve and spectra of the supernova, as well as the chemical enrichment of the interstellar medium. The first quiet irony is that the violent expulsion of the star's material is powered by processes that occur in complete darkness inside the core. The second is that the most dramatic transformation in the star's life is invisible until the shock reaches the surface, by which time the event is already irreversible. The third is that the debris that will drift cold and dark through space begins as a searing front moving at thousands of kilometers per second. The quiet mystery of the unbinding lies in the variability of the outcome. In some stars the shock leaves behind a neutron star, in others a black hole, and the factors that decide between these fates include the structure of the progenitor, the timing of the shock revival, the degree of asymmetry, and the amount of fallback. Fallback occurs when some of the ejected matter fails to escape the gravitational pull of the remnant and falls back onto it, potentially pushing a neutron star over the mass limit and causing it to collapse into a black hole. The degree of fallback can also alter the final chemical yields, swallowing heavy elements that would otherwise enrich space. As the shock nears the surface, it accelerates due to the steep density gradient, eventually breaking free in a burst of radiation known as shock breakout. For a red supergiant, the breakout may produce a brief but intense flash of ultraviolet light lasting an hour, while in a more compact progenitor such as a blue supergiant or stripped envelope star, the breakout may be shorter and harder, peaking in X-rays. Once the breakout has occurred, the expanding debris becomes visible in optical light, rising to peak brightness over days to weeks as it is heated by the decay of radioactive nickel-56 produced in the explosion. This decay to cobalt-56 and then to iron-56 powers the light curve long after the initial shock energy has faded. The distribution of nickel within the ejector, shaped by the mixing instabilities during the explosion, determines how quickly the light curve rises and how it declines. For weeks to months, the supernova remains one of the brightest objects in the sky of its host galaxy, easily outshining the combined light of billions of ordinary stars. The unbinding also sends a blast wave into the surrounding interstellar medium, compressing and heating it, and driving turbulence that can trigger new star formation. In some cases, the supernova expands into a cavity cleared by the progenitor's stellar wind, allowing the remnant to grow rapidly before slowing as it sweeps up more material. Over time, the remnant becomes a complex structure of shocked gas and magnetic fields, glowing in X-rays, radio waves, and optical light as electrons are accelerated to near-light speeds in the shock fronts. Yet for the star, the unbinding is the final loss of its identity as a coherent object. In the seconds after core collapse, the tightly ordered layers built over millions of years are disrupted, reversed, and scattered. Dense clumps rich in heavy elements race outward alongside shells of lighter gases, and the central remnant, if it remains, is left in near-perfect isolation, surrounded only by expanding vacuum and debris. In some explosions, the asymmetry of the shock imparts a recoil to the remnant, giving neutron stars space velocities of hundreds of kilometers per second, sending them on long journeys through the galaxy. The fact that the explosion can impart such a kick is evidence of the unevenness of the unbinding, even in an event that appears symmetric from afar. The unbinding of a star is not only a physical event, but also the start of the dispersal of its legacy. Elements forged in its core and during the explosion itself begin their long diffusion into the galaxy. Some will be incorporated into new stars and planets, some will remain in interstellar clouds for millions of years, some may be locked into grains of dust that travel between stellar systems. This cycle is slow, but the source is singular. Without supernovae, many of the elements necessary for rocky planets and life would be vanishingly rare. The irony is that the violent destruction of stars is essential for the gentle formation of worlds. Even as the supernova fades from view, the matter it cast into space continues to participate in the evolution of the galaxy. Long after the last photons from the explosion have been scattered, the remnant expands, cools, and merges into the interstellar medium. The space that once held a massive star becomes a region enriched and altered by its passing. The star's light, its matter, and even the empty cavity left by its removal all become part of the next chapter of cosmic history. The unbinding is not simply the end of the star, but the release of its contents into the shared reservoir from which new stars will form. In the moment of explosion, the star ceases to be itself, but in the debris that streams away, it becomes part of everything that will come after. The many faces of death in massive stars are distinguished not by the physics of collapse itself, which follows the same central script of iron core failure and shock revival, but by the outer layers present when the explosion occurs. The classification of core collapse supernovae into types 2, Ib and Eek, comes from the spectra of their light, which reveal the chemical composition of the ejected material. Type 2 supernovae show strong hydrogen lines, indicating that the progenitor retained much of its hydrogen envelope at the time of explosion. These are often the deaths of red supergiants, their vast cool envelopes producing a characteristic plateau in the light curve as the expanding hydrogen recombines over weeks to months. Type Ib supernovae lack hydrogen lines but display helium, the result of progenitors that have lost their hydrogen envelopes through stellar winds or mass transfer to a companion. Type Ick supernovae show neither hydrogen nor helium lines, indicating even more extensive stripping, often leaving only carbon and oxygen layers around the core. The essential fact is that these differences reflect the history of mass loss before collapse, shaped by initial mass, metallicity, rotation, and binarity. A lesser-known detail is that some massive stars lose their envelopes in violent eruptions during the last years or decades of life, possibly due to instabilities in the late burning stages. These outbursts can surround the star with dense shells of material that profoundly influence the appearance of the supernova if the ejecta collide with them. The first quiet irony is that the most massive stars, whose powerful winds are driven by their immense luminosities, can die looking smaller and more compact than stars of lower mass that keep their envelopes until the end. The second is that two explosions with identical core physics can appear entirely different to an observer, depending only on what layers the shock must pass through. The third is that the light curve of a supernova can be shaped more by the star's final years of slow loss than by the collapse that destroyed it. Type 2 supernovae themselves have subcategories. Type 2p, the most common, show a plateau in brightness as hydrogen recombines. Type 2l decline more linearly, possibly because of thinner hydrogen envelopes. Type 2n display narrow emission lines from dense circumstellar material interacting with the ejecta, producing bright, sometimes prolonged light curves. Interaction-powered events can outshine typical supernovae, their luminosity fed by the conversion of kinetic energy into radiation at the collision front. In extreme cases, these may be related to luminous blue variables, stars prone to giant eruptions that shed multiple solar masses in short times. For stripped envelope supernovae, the progenitors are often Wolf-Rayet stars, massive, hot, compact stars with strong winds, or stars in close binaries that have transferred mass to their companions. The stripping process changes the star's surface composition, removing hydrogen and often helium, and alters the density structure through which the shock must propagate. This can produce faster, more compact explosions with different spectral signatures. The quiet mystery is how frequently binary interaction plays the decisive role in creating type Zib and X. Observations suggest that many massive stars are in close binaries, and that a significant fraction of stripped envelope supernova may come from systems where the companion has shaped the progenitor's evolution. The interaction can leave behind a bright, hot star orbiting the compact remnant after the explosion, or in some cases the binary may be disrupted entirely, sending the survivor into the galaxy at high velocity. The diversity of outcomes extends beyond these types. Some core collapses produce unusually faint supernovae, perhaps due to weak explosions with significant fallback, while others produce hypernovae with energies several times higher than typical, often associated with long-duration gamma-ray bursts. In these rare events, rapid rotation and strong magnetic fields may drive jets along the rotation axis, piercing the star and releasing enormous amounts of energy. The jets can synthesize elements under extreme conditions, leaving distinct chemical signatures in the ejecta. In the most massive stars above roughly 100 solar masses, an entirely different fate can occur. Pair instability supernovae. In these stars at high core temperatures, energetic photons can convert into electron-positron pairs, reducing radiation pressure and triggering rapid contraction. The contraction ignites explosive oxygen burning, releasing enough energy to completely unbind the star, leaving no remnant. In slightly lower mass cases, pulsational pair instability can drive repeated partial explosions that eject large amounts of mass before final collapse. These events are rare in the modern universe, but may have been more common in the first generations of stars, which formed with low metallicity and could reach extreme masses. The observational challenge is that the many faces of core collapse can blur into one another when seen from great distances or when data are incomplete. Dust extinction can hide spectral features, and interaction with circumstellar material can mimic or mask intrinsic differences. The light we see is a combination of the explosion's intrinsic properties, the environment through which it propagates, and the viewing angle from which it is observed. Yet despite this variety, all core collapse supernovae share the same ultimate cause: the failure of the core to support itself once fusion has reached iron and beyond. The outer appearance is a reflection of the journey taken to that point, the losses and gains of mass, the presence or absence of a companion, the metallicity of the gas from which the star formed. The irony is that while the internal physics of collapse is governed by universal laws, the observer's experience of the event depends on contingencies that are almost incidental to the core's fate. In the silence before the explosion, the outer layers bear the imprint of millions of years of wind, eruption, and interaction, and it is these layers that will shape the light, colour, and duration of the last signal the star will send. Whether the death is wrapped in hydrogen, bared to carbon, or hidden inside a dense shroud of its own making, the core will collapse all the same, and the end will be swift. But to the galaxy, the many faces of death are a spectrum of enrichments, energies, and motions, each a distinct contribution to the shared matter from which the next stars will rise. When small stars borrow time, their endings take a different but no less final path. In systems where a white dwarf orbits close to a companion star, the white dwarf can draw matter from its partner through a steady stream or occasional bursts, adding mass that it could never have acquired on its own. This transfer can occur via Rochelobes overflow, where the companion's outer layers spill past a gravitational boundary into the white dwarf's grasp, or through the capture of material from the companion's stellar wind. The essential fact here is that if the white dwarf's mass grows toward the Chandrasekhar limit of about 1, 4 solar masses, the electron degeneracy pressure that supports it will fail, not because of gravitational collapse into a neutron star, but because the density and temperature ignite runaway thermonuclear burning of carbon and oxygen throughout the star. This thermonuclear disruption produces a type Ia supernova, which completely unbinds the white dwarf and leaves no remnant. A lesser-known detail is that there are at least 2 distinct pathways to this end. The single degenerate scenario, where a white dwarf accretes matter from a non-degenerate companion, such as a red giant or main-sequence star, and the double degenerate scenario, where 2 white dwarfs spiral together and merge due to gravitational wave emission, their combined mass exceeding the limit. The first quiet irony is that a star that has already exhausted its nuclear fuel and settled into a quiet inert state can be reawakened into the most luminous act of its existence by the gift, or burden, of borrowed mass. The second is that in this form of supernova, the explosion does not come from the collapse of the core but from its complete incineration, turning the entire star into expanding ash. The third is that such explosions, while destroying their source entirely, have become some of the most important tools in cosmology, serving as standardizable candles to measure the expansion of the universe. In the single degenerate channel, accretion must proceed at a rate that allows the white dwarf to grow in mass without igniting surface material prematurely. Too rapid a rate can cause nova eruptions that eject more mass than they add. Too slow a rate can let hydrogen accumulate and detonate in flashes without significantly increasing the star's mass. If the balance is maintained, the central density rises until the conditions for carbon fusion are met. In a degenerate core, pressure does not depend on temperature, so there is no expansion to moderate the reaction. Once ignition begins, the burning runs away in a fraction of a second, consuming the star in a detonation, or a combination of deflagration and detonation that sends matter racing outward at thousands of kilometers per second. In the double degenerate channel, 2 white dwarfs in a close binary lose orbital energy through gravitational waves, gradually drawing together over millions to billions of years. When they merge, the combined mass can exceed the limit, triggering runaway burning, or the violent merger process itself can ignite the explosion. The quiet mystery lies in the relative contributions of these 2 channels to the observed population of Type Ia supernovae. Evidence exists for both. Some show signs of interaction with a non-degenerate companion, while others lack such traces and fit the merger scenario better. The frequency of each pathway has implications for how these supernovae enrich galaxies and how reliably they can be used as distance indicators. The light curves of Type Ia supernovae are powered entirely by the decay of nickel-56 into cobalt-56 and then iron-56, and the amount of nickel produced determines the peak brightness. The uniformity of these explosions is remarkable given their varied origins, and empirical correlations between light curve shape and luminosity allow astronomers to use them to measure cosmic distances with precision. Yet this uniformity masks the underlying complexity, where differences in progenitor mass, composition, and explosion mechanism produce subtle variations. The irony is that the stability and usefulness of these events for cosmology rest on physical processes that remain incompletely understood. In galaxies, Type Ia supernovae are major contributors to the enrichment of iron and iron group elements in the interstellar medium. Their yields differ from those of core collapse supernovae, providing a distinct chemical signature that can be traced in the composition of stars. The timing of these explosions also affects galactic evolution. Because they can occur long after the formation of their progenitor stars, they provide delayed feedback that influences star formation rates and chemical mixing on billion-year timescales. In some cases, the interaction of the supernova ejector with a companion star can strip material from it, leaving behind a heated, fast-moving remnant that may be detectable long after the explosion. Such survivors, if found, would provide direct evidence for the single degenerate channel, but they remain rare in observations. The path to a Type Ia supernova is quiet until its final moment. White dwarfs are small, dense, and faint, their presence betrayed mainly by their gravitational influence or by the X-ray emission from accretion. Even in a close binary, the transfer of mass can be steady enough to escape notice until the threshold is crossed and the runaway begins. The explosion, when it comes, is global and final, every part of the star participating in the burning. No neutron star or black hole remains, only an expanding cloud of debris and the enrichment it carries. The destruction is absolute, but in that destruction, the white dwarf performs a last act of creation, sending elements into the galaxy and light into the deep sky where it will be used to trace the history of cosmic expansion. The irony is that such an event depends not on the star's own mass at birth, but on the companionship and orbital dynamics that can deliver the mass it needs to reach instability. A solitary white dwarf will cool forever into darkness, but in a binary, even one that began without any hint of violence, there is a pathway to a supernova written in the geometry of their orbit. When small stars borrow time, they can repay it in the currency of light visible across billions of light years, in explosions so similar in their glow that they have become mile markers in the universe, even as the details of their origins remain one of astrophysics' enduring puzzles. The limit of weight is set by a simple but unforgiving principle. When a stellar remnant supported by electron degeneracy pressure exceeds about 1.4 times the mass of the Sun, that pressure can no longer resist the inward pull of gravity. This threshold, known as the Chandrasekhar limit, applies to white dwarfs, which are the compact remains of stars that never reach the conditions for core collapse in life. In these remnants, electrons are squeezed into the smallest allowed quantum states, and it is this degeneracy, not heat, that holds the star up. But unlike thermal pressure, degeneracy pressure is independent of temperature. Adding mass increases density without producing the expansion that would relieve the compression. When the limit is approached, either by steady accretion from a companion or by merger with another white dwarf, The result is catastrophic instability. The essential fact here is that the Chandrasekhar limit is determined by the physics of quantum mechanics and special relativity together. At high densities, electrons move at speeds approaching that of light, and their momentum grows more slowly with increasing energy, weakening the pressure they can exert. A lesser-known detail is that for white dwarfs composed primarily of oxygen, neon and magnesium, exceeding the limit may not produce a thermonuclear type Ia explosion, but instead lead to collapse into a neutron star through electron capture, before temperatures become high enough for runaway burning. The first quiet irony is that this limit is the same everywhere in the universe, a universal ceiling written into the laws of matter itself. The second is that the very property that allows white dwarfs to exist at all, the resistance of electrons to being compressed, contains the condition for their destruction. The third is that the limit is not softened by time or distance. A white dwarf billions of years old can remain stable indefinitely until just the right amount of mass is added. The existence of this limit explains why stars born with initial masses below about 8 times that of the Sun can leave behind white dwarfs, rather than collapsing into neutron stars. For such stars, the core never becomes hot enough to fuse elements heavier than carbon and oxygen, and after losing their envelopes as planetary nebulae, they settle into long, cooling lives. But in binaries, where mass transfer is possible, the limit becomes a point of vulnerability. Even a small addition to the mass can push the star toward instability, and because degeneracy pressure does not depend on temperature, there is nothing to slow the progress once the density and composition cross the critical threshold. The quiet mystery lies in the details of the transition from stability to collapse or explosion. In some cases, as in carbon-oxygen white dwarfs, rising density ignites carbon fusion throughout the degenerate material, causing a thermonuclear runaway and unbinding the star entirely. In others, as in oxygen neon magnesium white dwarfs, the density triggers electron capture on magnesium and neon nuclei, reducing the number of electrons available to provide pressure support and driving collapse into a neutron star without a bright supernova. The observational differences between these paths can be subtle, and some may leave only faint or rapidly fading transients. The limit of weight also applies in a different form to neutron stars. For them, the degeneracy of neutrons and the repulsive nuclear forces provide support, but there is again a maximum mass, around 2 to 3 times that of the Sun, beyond which no known force can prevent collapse into a black hole. In this sense, the Chandrasekhar limit is the first in a series of mass thresholds that mark the boundaries between different kinds of stellar remnants. The white dwarf's limit is the most accessible to observation because of the role it plays in Type Ia supernovae, whose brightness and uniformity make them valuable for cosmology. Yet even here, uncertainties remain about how close to the limit a white dwarf must be before ignition occurs, and whether some explosions happen below the limit due to other instabilities. The irony is that the limit, calculated by Subrahmanyan Chandrasekhar in the early 1930s, was once the subject of intense debate, yet it has become one of the most firmly embedded constants in astrophysics, appearing in models from the life cycles of stars to the chemical evolution of galaxies. In the lives of white dwarfs, the limit is not approached in isolation. It is shaped by the interplay of mass transfer rates, composition, magnetic fields, and rotation. A rapidly rotating white dwarf can support more mass temporarily, delaying collapse or explosion, but loss of angular momentum over time will reduce this support and bring the star back toward the limit. Magnetic fields can channel accreted material and influence how it mixes with the underlying layers, affecting the likelihood of ignition. In the case of mergers, the dynamics of the collision determine whether the explosion occurs promptly, or whether a massive hot remnant survives for a time before crossing the limit. The universality of the limit does not make the outcomes uniform. What happens beyond it depends on the nature of the material, the thermal state of the core, and the environment of the star. But nothing can remove the limit itself. It is a quiet boundary, invisible in the remnant's light, waiting at the intersection of gravity and quantum mechanics. In the long arc of a white dwarf's existence, the limit of weight may never be reached. A solitary remnant can cool into near invisibility over trillions of years without approaching instability. Yet in the crowded environments of binaries, globular clusters, and merged systems, the limit becomes a constant test, a condition that may one day be met. When it is, the response will be swift, the transition irreversible, and the remnant's long stability will end either in the light of thermonuclear destruction or in the silence of collapse into a denser form. The quiet truth is that the Chandrasekhar limit is not a milestone on a journey, but a wall. For those white dwarfs that encounter it, there is no return. For those that do not, it is an unseen horizon, always present, always the same, even if never reached. The flash of Typeia begins deep inside a carbon-oxygen white dwarf, when conditions cross the critical threshold for runaway fusion. In the degenerate matter of the core, pressure does not depend on temperature, so there is no gentle expansion to moderate the reaction. Once carbon ignites, the heat cannot cause the star to swell and cool. Instead, it drives the temperature higher, accelerating the fusion rate in a feedback that races toward completion in seconds. The entire star becomes a site of thermonuclear burning, transforming carbon and oxygen into a mix of nickel-56, cobalt-56, iron-56, and intermediate mass elements such as silicon, sulfur, and calcium. The essential fact is that this process releases enough energy to completely unbind the star, sending the debris outward at velocities exceeding 10,000 kilometers per second, and leaves no compact remnant behind. A lesser-known detail is that the burning front may begin as a subsonic deflagration, moving through the star by thermal conduction, and then transition to a supersonic detonation, a process called deflagration to detonation transition. The relative timing and location of this transition strongly affect the composition and velocity structure of the ejector, shaping the light curve and spectral features observed from Earth. The first quiet irony is that the dead, inert star that has cooled in silence for billions of years can end its existence in one of the most brilliant explosions in the universe. The second is that the uniformity of these explosions, which allows them to be used as standard candles in cosmology, hides the diversity of physical paths that lead to them. The third is that the light we see, sustained for weeks, is powered not by the initial blast but by the radioactive decay of nickel-56 forged in the explosion. In the single degenerate pathway, the mass of the white dwarf grows steadily as it accretes matter from a companion star. As the core density rises above 2 billion kilograms per cubic meter, carbon fusion ignites near the center and the flame spreads outward. Convection before ignition may stir the interior, affecting the symmetry of the burning, but once the runaway begins, the process is unstoppable. In the double degenerate pathway, two white dwarfs spiral together due to gravitational wave emission and merge. If the merger is violent, a detonation may ignite promptly at the contact point. If more gradual, the remnant may survive for a time before collapsing or detonating. The quiet mystery lies in which of these pathways dominates in the universe. Population studies and the observed diversity of Typeia events suggest that both contribute, but their relative frequencies and the details of their ignition remain active areas of research. The explosion ejects about a solar mass of material, with the fraction of nickel-56 ranging from about 0.3 to 0.8 solar masses. The amount of nickel determines the peak luminosity, while the total ejected mass and opacity set the width of the light curve. The expansion quickly renders the debris optically thin in the outer layers, revealing the lines of intermediate mass elements, while the deeper layers dominated by iron group elements emerge later as the supernova fades. The uniformity of Type Ia light curves is not perfect. Some events are underluminous, perhaps from explosions of sub-Chandrasekhar mass, white dwarfs ignited by a helium shell detonation, while others are overluminous, possibly from mergers producing super-Chandrasekhar mass remnants before detonation. These outliers challenge the assumption that all Type Ia supernovae share identical origins, even as the majority remain remarkably consistent. From a galactic perspective, the role of these explosions is as important as their brightness. They are major sources of iron and iron peak elements, enriching the interstellar medium in ways distinct from core collapse supernovae. Because they can occur in populations of old stars, they extend chemical enrichment over long timescales, influencing the metallicity evolution of galaxies. The timing of their contribution can be traced in the elemental ratios of stars, providing a clock for galactic archaeology. In the moments after ignition, the flame front moves through the dense core, and the star's gravitational binding energy is overcome by the release from nuclear fusion. The expansion begins before the burning is complete, freezing in the distribution of elements according to the density at which they were formed. The debris races outward into interstellar space, colliding with any nearby material and driving shocks that can produce X-ray and radio emission years later. In systems with a non-degenerate companion, the ejector may strip material from it, and the collision itself may produce a brief early excess of light in the supernova's rise. Detecting such signatures can reveal the nature of the progenitor system, but they are subtle and often lost in the broader glow. The irony of the flash is that it is not the blast itself, but the decay of unstable nuclei that sustains the visible brightness. Nickel-56 decays to cobalt-56 with a half-life of about 6 days, and cobalt-56 decays to iron-56 with a half-life of about 77 days, each step releasing gamma rays that are absorbed by the expanding debris and re-emitted as optical light. As the ejector thin, more of the gamma rays escape directly, and the light curve declines. The transition from full trapping to transparency marks the fading of the event into the background light of its galaxy. Even after the light has faded, the remnant continues to expand for thousands of years, a bubble of iron-rich plasma slowly cooling and merging with the interstellar medium. In the Large Magellanic Cloud, the remnant of SN1006 still glows in X-rays, its shock front accelerating particles to near-light speeds. The material cast off in the flash will one day be part of new generations of stars and planets, carrying within it the iron that was the white dwarf's undoing. The quiet truth is that the flash of Type Ia is both an end and a beginning, an end to the compact stability of a degenerate star, and a beginning for the dispersal of elements that will seed future systems. It is an explosion whose causes are hidden from direct view, whose light is shaped by the isotopes it creates, and whose place in the universe's expansion has made it a tool for measuring distances on scales far beyond its own galaxy. Each one is both a local act of destruction and a cosmic beacon, uniform enough to map the universe yet diverse enough to keep its origins a matter of ongoing discovery. Rare paths and stranger ends unfold in the margins of stellar evolution, where initial masses, compositions, and physical conditions take stars away from the common routes to white dwarfs, neutron stars, or black holes. One of these rare outcomes is the electron capture supernova, which occurs in stars with initial masses of roughly 8 to 10 times that of the Sun. These stars develop oxygen-neon-magnesium cores supported by electron degeneracy pressure, but the cores never grow hot enough for neon burning to ignite before reaching the threshold where density triggers the capture of electrons by magnesium and neon nuclei. The removal of electrons robs the core of its primary source of pressure, and collapse follows swiftly, leading to a supernova that is less energetic than typical core collapse events, yet capable of producing a neutron star. The essential fact is that in these supernovae, the collapse is driven not by the formation of an inert iron core, but by the gradual erosion of electron degeneracy through capture reactions. A lesser-known detail is that electron capture supernovae may be associated with a specific class of relatively faint and rapidly evolving explosions, and their remnants may have unusually low kick velocities compared to those from standard core collapse. The first quiet irony is that these stars sit exactly on the boundary between quiet, fading into white dwarfs and violent collapse, so small differences in mass loss or composition can tip them from one fate to another. The second is that the collapse is triggered not by running out of nuclear fuel, but by a change in the accounting of particles that provide pressure. The third is that these relatively gentle explosions in energy terms may still forge heavy elements and alter the interstellar medium on large scales. Stranger still are the pair instability supernovae that can occur in stars with helium cores above about 60 solar masses, corresponding to initial masses above roughly 140 solar masses at low metallicity. In these massive stars, high-energy gamma rays in the core can produce electron-positron pairs, reducing radiation pressure and allowing the core to contract. The contraction raises the temperature further, igniting runaway oxygen burning that releases enough energy to completely disrupt the star. No remnant is left. All the mass is expelled into space in a single, extremely luminous event. Even more extreme is the pulsational pair instability regime, affecting stars with slightly lower helium core masses. In these stars, pair production still triggers contractions, but the resulting thermonuclear burning is not powerful enough to unbind the entire star. Instead, the star experiences repeated violent outbursts over years to decades, ejecting massive shells of material before eventually undergoing core collapse in a final supernova. The quiet mystery is how often such massive progenitors form in the modern universe, where higher metallicity drives stronger stellar winds that reduce mass before the core can reach the necessary size. Observations of some very luminous supernovae suggest that pair instability or pulsational pair instability processes may still occur in rare cases, particularly in low metallicity dwarf galaxies. Another unusual path is the fate of rapidly rotating, strongly magnetized massive stars that may produce long-duration gamma-ray bursts when they collapse. In these cases, rotation and magnetic fields channel the collapse into narrow relativistic jets that punch through the star, releasing extreme amounts of energy along their axes. Such events are rare because they require a delicate balance. Enough rotation to form an accretion disk around the newborn black hole or neutron star, but not so much angular momentum lost to winds before collapse. The bursts are fleeting, but their afterglows and host galaxies offer clues to the conditions needed for such explosions. The first quiet irony here is that these events may appear far more energetic than typical supernovae, yet their power is concentrated into narrow beams, meaning most of the energy misses most of the universe. The second is that the apparent brightness to an observer depends almost entirely on whether they happen to lie within the beam's path. The third is that the same mechanisms that make the explosion extreme also make it rare, stripping away nearly all but the most unusual progenitors. Some rare end states are determined not just by mass but by environment. Stars in dense clusters can undergo collisions and mergers during their lifetimes, producing rejuvenated massive stars or even stellar masses above what isolated star formation would allow. These products may follow paths to explosion that are otherwise inaccessible, including supermassive pair instability events or unusual core structures that change the explosion dynamics. The quiet truth of all these rare paths is that while they represent only a small fraction of stellar deaths, they can have disproportionate effects on their surroundings. Pair instability supernovae, for example, release several times more mass and energy than typical core collapse, dramatically enriching and disturbing their host galaxies. Electron capture supernovae may contribute specific isotopes to the interstellar medium in ways that shape chemical evolution. Magnetorotational explosions may seed distant regions with heavy R process elements such as gold and uranium. These stranger ends are also important for what they reveal about the limits of stellar models. Each is a test of how physics behaves under extreme density, temperature, and composition. Each carries uncertainties about mass loss rates, nuclear reaction rates, rotation, magnetic field evolution, that ripple into predictions for more common stellar fates. And each serves as a reminder that stellar evolution is not a single smooth progression, but a branching structure where small changes in the early stages can send stars toward very different destinations. In the great balance of stellar births and deaths, the rare paths are exceptions, but in the history of galaxies they leave indelible marks. Unusually large cavities in the interstellar medium, distinctive patterns in elemental abundances, and occasionally light curves so bright they can be seen across most of the observable universe. They are the statistical outliers that prove the rules of stellar evolution while also challenging them, forcing refinements to theory and inspiring the search for progenitors in the farthest and faintest reaches of space. Seeds for future suns are sown in the debris of a supernova, where the elements forged over a star's lifetime and in the violence of its death are cast into the interstellar medium. The shock wave from the explosion expands into the surrounding space, sweeping up gas and dust, compressing some regions while dispersing others. The essential fact is that supernovae are the primary sources of many of the heavy elements in the universe, from oxygen and silicon to iron, nickel, and beyond, and without them the material for rocky planets and complex chemistry would be scarce. A lesser-known detail is that the ejecta also contain radioactive isotopes, such as aluminum-26 and iron-60, which decay over timescales of hundreds of thousands to millions of years, releasing heat that can influence the thermal evolution of newly forming planetary bodies. The first quiet irony is that the destruction of a star is also an act of creation, enriching the galaxy so that future stars can form with a richer composition than their predecessors. The second is that the violence that clears and stirs the interstellar medium can also trigger the collapse of nearby clouds, setting in motion the birth of new stars. The third is that in the chaos of the explosion's aftermath, the material that once lay deep in a stellar core becomes part of diffuse clouds that may one day collapse into ordered systems. As the remnant expands, it passes through distinct stages. In the free expansion phase, the ejecta move at thousands of kilometers per second, hardly slowed by the surrounding medium. This lasts for a few hundred years until the mass of swept-up interstellar matter becomes comparable to the mass of the ejecta. The remnant then enters the Seedoff-Taylor phase, where its evolution is dominated by the conversion of kinetic energy into heat, as the shock wave slows and the hot gas inside maintains high pressure. During this phase, lasting tens of thousands of years, the remnant glows brightly in X-rays, and turbulence and instabilities can mix the ejecta with the surrounding gas. Eventually, radiative cooling becomes efficient, and the remnant enters the snowplow phase, where the shock front compresses the gas into a dense shell that moves outward more slowly, finally merging with the interstellar medium. The quiet mystery is how much of the newly synthesized material escapes into the galaxy versus how much is locked into dust grains that may be destroyed by the shocks themselves. Observations show that supernovae can produce significant amounts of dust, but the survival of this dust through the harsh conditions of the remnant's expansion is uncertain, especially in the face of reverse shocks that move back into the ejector and destroy fragile grains. Some fraction of the heavy elements condense into solid particles that can serve as the cores of future planets, comets, and asteroids. Meteorites in our own solar system contain isotopic signatures that trace their origins to specific nucleosynthetic processes in ancient supernovae, evidence that our planetary system inherited material from multiple stellar deaths. In regions where multiple massive stars form in clusters, the overlapping winds and supernovae can carve out superbubbles, vast cavities of hot, tenuous gas surrounded by dense shells. Within these shells, compression can ignite new episodes of star formation while the interior remains a reservoir of enriched gas. This cyclical process ties the lives of massive stars directly to the birth of new generations. Over millions of years, the metals dispersed by supernovae mix into the broader interstellar medium, raising the metallicity of the galaxy. This gradual enrichment changes the cooling properties of gas clouds, allowing them to fragment more efficiently and form lower mass stars than the nearly metal-free clouds of the early universe. In this way, each generation of stars influences the characteristics of the next, with supernovae as the main agents of change. The irony is that the same blast that can erase fragile structures in a molecular cloud can also set the stage for their replacement with new ones, often richer and more complex. The mixing of elements from many different progenitors ensures that each new star contains a blend of material from countless ancestors. The hydrogen and helium remain from the Big Bang, but the carbon in organic molecules, the silicon in rocky crusts, the iron in planetary cores, and the heavier trace elements all owe their existence to stars that died long before. In some regions, the link between death and birth is immediate. The shock from a nearby supernova can overrun a dense clump in a molecular cloud, compressing it enough to trigger gravitational collapse. Such events may have played a role in the formation of our own solar system, as suggested by isotopic anomalies in ancient meteorites that point to the injection of short-lived radionuclides into the protoplanetary disk. Even without such direct triggering, the enrichment from previous generations is present in the gas that forms every new star. Over galactic timescales, the seeds sown by supernovae accumulate, making each round of star formation more chemically complex. The result is a galaxy where young stars and planets can form with the ingredients for diverse chemistry, including the elements necessary for life as we know it. Yet these seeds are not sown evenly. Regions with more intense star formation, such as spiral arms or starburst galaxies, experience higher rates of supernovae and faster enrichment, while more quiescent regions change more slowly. The history of supernova activity is written into the chemical composition of stars, allowing astronomers to trace the evolution of galaxies by measuring elemental abundances. The quiet truth is that in scattering their contents, supernovae erase themselves as individual objects but become part of everything that follows. A remnant fades, its shape dissolves, its energy disperses, but the atoms it carried remain, cycling through clouds, stars, and planets over billions of years. The seeds for future suns are sown in the ashes of those that came before, in a continuity that links the most violent ends to the most gentle beginnings.